This video is the second video in the equilibrium unit, and it's about the equilibrium constant Kp. What we're looking at now is the equilibrium constant Kp, and the K that we were looking at in the video prior to this one would technically be Kc, because we were dealing all with molarities, which is concentration. So that C stands for concentrations, right? But with gases, it's not always that easy to calculate the molarities. It's much more easy to calculate the pressure. And so a lot of the time, gases' concentrations are represented as partial pressures. And so because of that, we a lot of the time want to express it with the pressures. And so we have Kp. And so the little p just means pressure. And instead of brackets, we can use parentheses here, but we have to put that it's the pressure of NO2. And so for the equilibrium expression for this reaction, we would have the pressure of NO2, and then that would be squared because we have two of these, divided by the pressure of N2O4 raised to the first power because there's only one. So it's the exact same thing, but instead of having brackets, so Kc for this reaction would be the concentration of NO2 squared divided by the concentration of N2O4. And so, but these would have to be molarities, while these can be pressures in ATM, all right, or atmospheres. All right, so the relationship between Kp and Kc, there's an actual relationship where Kp will be equal to Kc times RT raised to the delta N. So you already know R. R is the universal gas constant, and the value is 0.08206, and the units are liter ATM over mole Kelvin, which you don't need because Ks don't have units. But the way that I remember it, that's the R that I use for this, is because it has ATM and pressures are in ATM. And then temperature always has to be in Kelvin because your R has the Kelvin value in it. So don't put it in Celsius, ever, never in Celsius. All right. And then delta N is always moles. And since we're talking about moles of a gas here, you can see moles of gas product minus moles of gas reactant. So it's the change in the moles of gas only. All right, so final moles of gas minus initial moles of gas. So in this first example, it says, what is the Kp at 1000 Kelvin if the partial pressures in an equilibrium mixture at 1000 Kelvin are 0.2 atm of CH4, 0.25 atm of H2S, and 0.52 atm CS2, 0.1 atm of H2. So the equilibrium expression for Kp would be partial pressure of H2 raised to the fourth times the partial pressure of CS2. Now remember, they have to be gases if they're going to have a pressure. Your solid isn't going to have pressure on it. Neither will something aqueous. And then CH4 is to the first. So that's the expression, and then I'm just going to plug all my values in. So I have 0.10 to the fourth, and that's this one. And then CS2, 0.52, and that is that one. And then 0.25 of H2S is going to be squared, and then 0.2 of CH4. Okay, so if I put that all into my calculator and I actually do it correctly, I will end up with 4.2 times 10 to the negative third. So that's it. That's the value. All right, for the reaction above, the Kp at 25 degrees Celsius is 1.9 times 10 to the third. And we want to know the value of Kc. So Kp is equal to Kc times RT raised to the delta N. That was the equation that we used. And what I want you to notice right here, right now, is that it's only RT raised to the delta N. Okay, Kc is not raised to the delta N at all. All right, and so we want to find this. We want to find that value, and we're given Kp, and then we have the rest of it. All right, so Kp is 1.9 times 10 to the third, and that's equal to Kc. And then the R that we use is 0.08206, And then my T has to be in Kelvin, and right now it's in Celsius. So to get to Kelvin, you take 273 and you add it to 25, and so that's 298. So we have 298 Kelvin, and then my delta N. So delta N is moles of product that are gases minus moles of reactant, and it's for gases only. Okay, so if I look here, for moles of product, I've got 2 moles of product, gas, and then over here I've got 2 and 1, so that's 3. So it's going to be 2 minus 3, or negative 1. So I end up getting 4.0893 times 10 to the negative 6. And that's times Kc, and that's equal to 1.9 times 10 to the third. So I'm going to divide both sides by this. These cancel out, and I end up getting 4.646 times 10 to the fourth. So we would round that to 4.6. So that's the Kc when my Kp is this, and I have a negative 1 change in moles of gas. All right, and then for this next one, we have Kc this time equal to 3.8 times 10 to the negative third, and a temperature of 1000 Kelvin, so I don't have to change that. So I'm looking for Kp. There's my R and my T. All right, and then my change in moles of gas. So I have 2, right, because 1 and 1. And then I have 4 for product. So it's going to be 4 minus 2, which is 2. So this is squared. So my answer ends up being 26. So where students usually mess up is, one, they won't convert Celsius to Kelvin, or they don't do this correctly. Guys, delta always means final minus initial. We're talking about pressures and gases. Final is going to be product. So it's final minus initial, or product minus reactant. It's the same thing. So you always look at their sum of your moles of gas product minus the sum of your moles of gas reactant. And if you can do that, then you can get this.